All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. It has been a while. Hopefully you guys are doing well. Hopefully you had a good Thanksgiving. Miss you guys. Feel like it's been forever. I don't think I remember how to write on a tablet or anything, but we'll get through it. So before we start, just a reminder, we have our second test on Friday. So make sure you're ready for that. And I already told you when the final exam was. I had the date earlier. I don't remember. I already did tell you when the final. Does anyone remember when the final is?
It's Monday the 14th at 5:30 p.m. Eastern.
Okay, awesome. Good. Thank goodness one of us is paying attention. How was your Thanksgiving? How did you guys do? I know a few of you flew out to family and stuff. How about the rest of you?
I just came home and spent it with my family. How was yours?
Ah, that was nice. I had dinner with family as well, but just locally. Yeah, it was good. I was also pretty busy, but that's nice. Okay, so we're all alive. It looks like most of us are here. So let's actually jump into this. I guess the rest of you are okay. Okay, awesome. Right. Yeah, the tests are going to be very similar. So it's the same format. So it's on Gradescope. So you will have to upload pictures of your work as well. And you can get partial credit from that. And the final is going to be pretty much like the tests as well, but just longer. So it's going to almost pretty much be a combination of test 1 and test 2. Any other questions about the test? So yeah, I'm going to write the test to be able to last an hour, but just like last time, I'll give you guys 75 minutes. So I'll start it 15 minutes early, just for technical difficulties and things of that sort. Yeah. Also be aware that you can be logged into Gradescope from your phone as well as your laptop. So that way you can actually move faster. So you can take pictures and upload your work with your phone while you're reading from the laptop working on another problem. Although uploading pictures shouldn't take that long. I've taken tests on Gradescope where we had to upload videos as well, and that took a while. So I was uploading it on my phone while I was working on other problems. So you can actually do that to cut down on time. Yeah, I don't think anything else. Hopefully you guys got together in your groups already and you guys have been studying together. The test, I expect it to be, it's going to be 12 to 15 problems, mixture of conceptual as well as stuff that you'd have to work out. So there will be a few problems that are hopefully relatively very quick for you to figure out and you won't have to do many calculations for. And then there are going to be some where you have to do calculations. I think it's going to be in the ballpark, 12 to 15 problems, maybe several parts each for a few of them. Yeah. Any other questions on that?
This is on Friday?
This is on Friday, yes, correct.
Okay.
So the test officially covers whatever I get up to today. Today is, I don't know how far I'm going to get, but I'm actually excited to get towards the end of the class, actually. But we're going to do something that I think it's fun. It's interesting. We're going to learn about vectors. Some of you probably know about vectors already from high school physics or whatever. Maybe even high school math class, you guys probably talked about vectors. And I don't know if is there anyone taking physics currently? Oh, nice. So you guys are going to know everything already. So Is there anyone not taking physics? Are you guys all in sciences and you're all doing physics and chemistry? Okay. Well, if you're not taking physics, don't worry about it. We are going to, again, start from scratch. I'm going to tell you what a vector is from the very beginning. So those of you who are in physics and you know about vectors, you probably roll your eyes and whatever, but I'll move quick and so as to make it exciting. And towards the end, I'm going to, hopefully I can get there. I want to actually set us up for the next topics that we're going to do, which are called vector and dot products and cross products. But I want to set up a more organic approach, or a more something where it's motivated, where you can see where the definitions are coming from, which usually they don't do that in a class. So some of you probably, you know what a dot product is, and you know what a cross product is, you know how to calculate, you know how to compute it. But where did it come from? Hopefully I'll get to talk a little bit about that towards the end of the class, which should be interesting. I think it'll be nice. But for the first part, we're going to talk about just vectors, what they are, why we need them, and how to do math with them. So here's where we are. We're in phase 4 of the class, 3D and vector stuff. Last time we introduced 3D space. We introduced the rectangular coordinate system, the X, Y, and Z axis, the XZ plane, the YZ plane, the XY plane, and how we someone's trying to get in, and how 3-dimensional space is set up mathematically. We spoke about the 8 octants. The first octant is the most important one. That's where all the coordinates are positive in value. We also spoke about planes, or the fact that something like x equals a constant, y equals a constant, or z equals a constant are planes. We practiced sketching them. We learned that something like x squared plus y squared equals 1 is actually a cylinder as opposed to a circle. And things like x equals 1 is actually a plane as opposed to a line, which we've always thought about. We looked at equations of spheres. We learned that the distance formula works out the same in 3 dimensions. And we looked at regions in 3 space, and we sketched a bunch of them. Being able to do something like this is going to be very important in the next class as well. But we started very slow, went from scratch, built everything up. So this is our world now. And it turns out that, as you can see, several things changed when we went from 2 dimensions to 3 dimensions. So for example, again, if you were to ask anyone in Calc 1 or below, what is x equals 1? Everyone's going to tell you, well, that's a line. Well, we learned that that's not true. It's actually a plane, right? So we also learned x squared plus y squared equals 1. Ask anyone in Calc 1 or below, that's a circle. But we know it's actually a cylinder. So it turns out that a lot of the language that we used in Calc 2 and a lot of the ways we thought about things weren't exactly correct in a more general sense. And we're going to want to be able to navigate in a more general sense in 3 dimensions and higher. And it turns out that vectors are very good at doing just that. And once you actually learn how to describe objects such as lines and surfaces and planes in terms of vector functions, then that is actually so good and so comprehensive that you never need to set things up again by moving to a higher dimension. Once you learn how to deal with vectors in 3D, then if you go to 4D, all the math stays the same. You just add another component to your vector. And so vectors are very nice. We're not going to talk about vector functions in this class. That's something you're going to talk about in the next class. To even talk about vector functions and things of that sort, we need to know what are vectors themselves. So just in the same way, before we can talk about the coordinates on a graph, we have to know about its coordinates. We have to know about what is a point and how do we identify a location. And that was a coordinate system. So we're going to kind of do the same thing. Vectors is going to provide the language for us to understand and interpret things, to calculate things. And so we really need to understand vectors themselves. And so that brings us to the next section, 12.2. Let me make this a little bigger. Okay, So this is going to be our introduction to vectors. And I know a lot of you know about this already, so I'll move relatively quickly. But again, if you have any questions, just stop me and ask me. Okay. All right. So as I mentioned, why we care about vectors is going to be a good way to describe things that are going on in space. And once we learn about 3-space, the jump from 2-space to 3-space is relatively steep. However, once you're in 3-space, to go from 3-space to 4-space or 5-space or infinite spaces, infinite dimensional spaces, it's actually mathematically relatively easy. You lose visualization once you go to 4-space or higher. You can't pictorially imagine anything anymore, but mathematically the computation is very easy and it falls in line with what we would have learned in 3-space. So vectors are very useful for that. So what is a vector? A vector, and for those of you who are math majors and you're going to a class like linear algebra or abstract algebra, it's going to be different. But for now, a vector is a quantity that has both magnitude and dimension, right? By the way, some of you might already know this. Quantities with only magnitude, we call these guys scalars, right? So if you want to describe something in terms of magnitude and direction, you have what you call a vector. These guys are usually represented by directed line segments or arrows like so. So we have, boom, there's your vector. It turns out that the tail here, this is called the initial point. The head here, this is called the terminal point. Clearly, this has a direction up and to the right, and we'll make that a little bit more precise pretty soon. And the length of this arrow is actually pretty important. The length here is called the magnitude of the vector. So a vector is just some kind of conceptualization of something that has magnitude and direction. So you can tell what direction it's moving in and how big it is at the same time. Okay, so that's that. So it's kind of like weight is a magnitude. I can talk about 2 pounds, and the direction when it comes to 2 pounds doesn't really make any sense. However, if I talk about force, like the force of gravity or the force that this car engine is putting out, a direction is definitely implied. The force of gravity pulls down. And so if I'm talking about a force, a vector is a better way to describe a force than just a magnitude. So yes, I can tell you that, you know, I hit you with a force of 5,000 newtons, but the direction where I hit you is going to matter, right? So whenever you want to identify magnitude and direction, vector is how you do it. And that's pretty much what a vector is, okay? So yeah, now we can name vectors. So if I have a vector here, I can actually give it a name. So I can call it here, I can say, this is the vector A, and I put a little arrow on top of it to indicate a vector. So when you're looking at vectors, you can either do it as a boldface, which of course, if you're writing by hand, no one's going to take the time to make it bold, or you can write a little arrow over it to indicate. And be aware that if I write A, it's not the same as me writing A. There's going to come a point in, and usually only math major will get to this point, where there comes a point where you don't even make a distinction between a vector or a regular variable. But for now, I want us to make a distinction. It's going to be very important for you to distinguish when you're talking about vectors as opposed to something else. Otherwise, you're going to get yourself confused. So this guy here, this is a scalar. This guy here represents a vector. So A is just some variable. It's a scalar variable. And A with a little arrow over it is a vector quantity. So it's a vector A. Now we can get a little bit more precise. So I can say, well, if I'm going from a point here, which is a point A, so let's say that's x1, y1, z1, and it ends at a point B, let's say that's x2, y2, z2, then I can call this vector the vector AB with an arrow like that. So you can actually name a vector based on the points that the vector passes through. So if you know the initial point and the terminal point, and you give those names, you can actually put the names beside each other, write an arrow over it, and it tells you that it's a vector going from this point to that point. Equality and position vectors. Now, one thing I want you to realize is that vectors are uniquely determined by their magnitude and direction. So in general, it doesn't matter where a vector is. The same vector can be at different locations. So what do I mean by that? Well, let's say here, we're in the XY plane. So let's say I have a vector right here that has a magnitude of 1, and it's at a 45-degree angle to the horizontal. And I have another vector over here in space. It also has a magnitude of 1, and it's at a 45-degree angle. Then, as far as I'm concerned, or anyone else, these are the same vector. So vectors themselves, yes, they talk about magnitude and direction, but they're not location dependent. If you're moving at 45-degree angle to the horizontal and you're moving up and to the right and you have length 1, you are the vector, right? Everyone would agree that this is the same vector. Now, there are some times when we actually need to position our vectors in some way to make sense of things. And whenever we do that, we say we have a position vector. A vector where the initial point is the origin specifically is called a position vector. So this also has length 1. This is at 45 degrees. So if this is a vector A, this is also a vector A. This here, I would call it specifically the position vector A. Right? So if someone mentions a position vector, they're specifically thinking as the initial point is the origin. But in general, a vector, it doesn't matter. Right? So you're not going to actually change the vector by where you are. So that's also important to know. So that's because sometimes it's necessary to have a common reference point. Okay, so yeah, so we did that. What else do I want to talk about here? I wrote these notes a long time ago. Let me remember my train of thought. Okay, yeah. So the next thing I want to talk about is how we can call these vectors. And I want to talk about mathematical notation of vectors. It turns out that position vectors, you can actually consider them somehow to be equivalent to points or coordinates in n space. And what does that mean? So let's say I have a vector, a point in space, a1, comma a2. So this is a point. Then if I have a position vector from this going to that point, boom, then I would call that vector. I can also call that vector a1, comma a2, but I would put angled brackets around it. And again, there's going to come a point where you're not going to distinguish between coordinates and vectors. But for now, I think it's very good that you distinguish between them. Because otherwise, when you're just learning about this stuff, you will get confused if you are thinking of something as a point versus a vector. So normally we don't think of coordinates as having any magnitudes associated with them. But there are going to be times when you definitely want to consider the distance from the origin to a certain point as opposed to just the point itself. And so you might want to think of a coordinate as a vector specifically. But once you actually can do that, you can actually write down the coordinate itself as a vector by writing an angled bracket. And what that means is there's a vector going from the origin to that coordinate. Yeah. Another thing that I can mention here is that if I write A1 comma A2, you can interpret this as this is how much we move in the X direction and versus how much we move in the Y direction. Right? Same way you'd think of a coordinate. A1 comma A2 means I move A1 units in the X direction and then A2 units in the Y direction, and then the vector just moves from like that. So the vector can be equivalent to telling you how you move in a position-wise. And so we get this sort of notation. So a two-dimensional vector whose terminal point is A1 comma A2, I can denote it by A1 comma A2 with angled brackets. Similar in three space, A1 comma A2 comma A3, I can think of it like that. And of course, in n space, we're not going to do n space. We're going as far as three space. You can actually do like that. So this is a two-dimensional, a three-dimensional, and an n-dimensional vector specifically, okay, respectively. So now you can also name the coordinates based on the variable that describes that component in whatever space you're looking at. So if we're in 2 and 3 space, the two coordinates are usually the X and Y coordinates. So you can actually talk about that. So the first coordinate in a vector is the X coordinate. The second coordinate in a vector is the Y coordinate. And the third coordinate in a vector is the Z coordinate. Okay. So for example, here, how can I sketch the vector 1 comma minus 2 comma 3? Well, remember how we drew 3 space? Okay. We're going to need a negative y there, negative x there. Dun, 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 dun. So again, you're going to move 1 unit on the x, minus 2 units in the y, and then 3 units in the z. So you're going to move here, then there, then up, right? And then that's going to be the vector moving like so. And that is going to be the vector 1 comma minus 2 comma 3. And there's going to be a coordinate here, which is the coordinate 1 comma minus 2 comma 3. And again, if I have any other vector where I had to move 1 unit this way, 2 units that way, and then 3 units up, is actually going to be also be equivalent to that. I can also call this vector 1 comma minus 2 comma 3. Okay, so hopefully that's clear. And again, if I say anything that's crazy or not clear, please stop me. Everyone with me so far? Are we good? Okay. All right, so we're going to need to know about talking about vectors from one coordinate to another. So let's say I know the initial point is x1 comma y1 comma z1, and the final point is x2 comma y2 comma z2. Then the position vector can be written as the vector AB is x2 minus x1 comma y2 minus y1 comma z2 minus z1. And so this is a way that we can actually write down a vector in shorthand notation. So if I am at the point 4 comma minus 2, I did forget how to write on this thing, 4 comma minus 2 comma 0, and there's another point here, 1 comma 3 comma 5, and I want the vector that goes from here to there, right? So this is the vector A. How can I describe the vector A? Well, the distance I move in the x direction is just the difference in distances, right? It's going to be x2 minus x1. The distance in the y is going to be y2 minus y1. The distance in the z is going to be z2 minus z1. Same way you measure distances, right? Right minus left, top minus bottom. So this by above AB, let's call it A, where this is A, that's B. This is just going to be the final minus initial, the final y coordinate minus the initial y coordinate, and the final z coordinate minus the initial z coordinate. So you have minus 3, 5, 5. So this is the vector minus 3, 5, 5. Okay, so I can create a vector that connects 2 points. It's going to be super important in the next class. So that's how you'd actually create a vector. So if I know 2 coordinates and I want to move from one to the other, I can create a vector that goes from one to the other. And essentially, this is how we're going to make up vector functions, believe it or not. You're just seeing the basic building block. So essentially, when we have a curve in space, essentially what we're going to do is we're going to think of a vector leaving the origin and hitting points on that curve, and it traces out the curve like a very long pen. And once we know how to describe a curve like that, then the interpretation of that curve is never going to change, even if you go to higher dimensions. It's not like how in 2 space, x equals 1 is a line. Suddenly in 3 space, what? This is a plane now? How did we go from a line to a plane? The same equation. The equation didn't change, the interpretation changed. With vectors, you're not going to run into that. So, and this is a basic building block of how you can get there. So that's pretty much nice. Let's talk about properties of vectors. So I spoke about a vector is something where you want to describe magnitude and direction. Overall, I think we've done a good job with talking about direction. I can know where it starts, where it ends, so I can tell you what direction it's moving in. So essentially, just the notation of me writing down a vector can already indicate to you what direction we're going in. But now, what if you want to talk about the magnitude of that vector? Well, the magnitude is given by this formula. It's the square root of the sum of the components, each squared. And that follows from Pythagoras' theorem, essentially. So it's by the distance formula. So again, if I wanted to find the length of the vector that I did above, right? So let's say I wanted to find the magnitude of this vector. How long is it? Well, the length here magnitude equals d. And we know by the distance formula, your d is going to be the square root of I'm going to have too many colors here. Let me make that black. Let me make this blue. Let me make this red. Let me make this, since it's known already, black. Okay, so I want D. So the distance formula says and we covered this last time, right? When we were talking about the equation of a sphere. It's the difference in all the components. So it's going to be x2 minus x1, y2 minus y1, z2 minus z1. And of course, you'll notice that that's literally the same formula that we use to actually create the vector in the first place, each component, x2 minus x1, y2 minus y1, z2 minus z1. And so pretty much what we're going to have, and I can even recompute it here, but you're going to notice that it's just going to be the components of A. In this case, the x2, y2, and z2 are the red coordinates. So this is going to be 1, 3, 5. Then I'm going to subtract the blue coordinates, 4, minus 2, 0. So you're going to have minus 3, 5, and 5. And you can note, these are the components of A. And so in this case, that's going to be square root of 59, it looks like. Okay, so that's actually the length of a vector. So you pretty much, you square each component. So next time from now on, when finding magnitude, you can just jump to here. Maybe I'll put that after. When finding magnitudes, we can jump to here. And so that's how you find the magnitude of a vector. And it's really a consequence of the distance formula, which itself is a consequence of Pythagoras' theorem. Okay, now let's actually talk about operations on vectors. Any questions on the magnitude? Okay, let's talk about operations on vectors, okay, and some of their geometric meanings. So it turns out we can do mathematics with vectors, kind of like how we can do with numbers. We can add them and do all sorts of things with them. We can't do everything. So you're going to notice that there's no real way to multiply vectors, even though we're going to talk about something called a vector product, but it's not going to be analogous to multiplication of numbers. There's no such thing as division of vectors, by the way. So even when we create a vector product, there's not going to be a way to dissect the members of that product, right? So it's kind of like if I took 2 times 3 and I get 6, I can always divide out the 3 to get back the 2, right? And I can see that the 6 was composed of a 2 and a 3. There's no such notion for vectors. Once you combine them in a product, quote unquote, you can't actually recover the original vectors that created that guy. So vectors, multiplication and division isn't defined. So there's something called a vector product that we can define. However, multiplication and division are not. However, there is something, there is an analogous notion to addition. We can add vectors, we can subtract vectors. So addition and subtraction are defined. So that's defined here. It's also defined very naturally. You actually add or subtract the corresponding components. We also have an operation called scalar multiplication. So scalar multiplication just means you multiply that vector by a scalar. So remember, a scalar is just a magnitude. So in other words, you can take a number, like in this case, I use the number c, just represents some random constant, and I can multiply the vector a1, comma a2, comma a3. And the result is to just multiply the corresponding components. So the vector CA is just the vector C times A1, comma C times A2, comma C times A3. So these are operations where I can combine 2 vectors to get a third vector. So I can take the vector A and the vector B and combine them by addition, and I can get a third vector, the vector A plus B. And I can subtract them, A minus B, which we'll talk about in a little bit. And I can get a third vector. I can take a vector and a scalar and I can combine them to get another vector in this way by scalar multiplication. And these all have uses. Some things you should note here, which at the moment I'm not going to dwell on, but you should just be aware of this. If your scalar is greater than 0, then CA will have the same direction as A. If your C is less than 0, then CA will have the opposite direction. So multiplying by a negative flips the vector in literally the opposite direction, which makes a lot of sense, right? If you think of multiplying each component by a negative, so if the X component was positive, then it became negative. It means instead of going right, you're now going to go left. And this happens in each component. So multiplying a vector by a negative changes the direction. So that's a geometric interpretation. If your C equals 0, you get to what's called this 0 vector. So it's 0 with a little arrow over it, or a bold 0. This is a very important and very mysterious vector. It's a vector that has no real direction, which kind of defeats the point, right? So it's like a vector with no direction. It points in literally every direction and no direction at the same time. It's a whole other beast. You'll talk about it more in your future math classes, but we will leave that here. Also worthy of note is that the length of the vector CA is just going to be the magnitude of C times the magnitude of A. And by the way, the magnitude, I should have mentioned it here. We use absolute values to write that down in notation. Sometimes people use double absolute values when they're talking about the magnitude of a vector, but it's not necessary. Once you have the arrow over the A, the absolute values, everyone takes this interpretation of that notation. So you can use single absolute values or double absolute values, it doesn't matter. Some people just like to emphasize, I'm talking about the magnitude of a vector, not the magnitude of a scalar. But once you have the little arrow over the A, everyone knows what you mean. So if you did not have the arrow over the A, then there might be a chance for confusion. So that's why they invented it, because later on, math people just get too lazy or something, I don't know. We stop writing the arrows. And then if I write absolute value of A, how do you know if that's actually something I need the distance formula for versus, oh, it's just like regular absolute value. Okay, but for us, it's not going to make a difference because for you guys, I need you guys to write the arrows over the A's if they are vectors. And A plus B is sometimes called the resultant vector. That might also be a language that you heard in your physics class. And let's look at what addition means. So the vector A plus B has the initial point of A and the final point of B. Essentially, how you think about it is, let's say my A is this guy and my B is this guy. Then how do you interpret A plus B? Well, you would start off with A, then to the terminal point of A, you attach the initial point of B, and then you head in the direction of B. And so if you go from the initial point of A to the final point of B, a vector that does that is called the vector A plus B. So this vector here, this is the vector A plus B. Now, there are tons of ways that you can get that, but that's one of the main definitions. You can also think about it as the diagonal of a parallelogram. So if you have a parallelogram where one side is A and the other side is moving along the direction of B, then A plus B is going to be the diagonal moving in this way. Now, as I mentioned, negating flips direction. So if I have, say, my A here, then minus A is going to flip it upside down. 2A is going to have the same direction of A, but it's twice the length. Minus 2A is going to have the same flip the opposite. So same direction as A. 2 times the length. This, by the way, is why we sometimes call constants scalars, because what they do to scale is to stretch or shrink. So multiplying by a constant scales a vector. So this is why we call constants scalars. And if I multiply by a negative constant, it negative scalars flip direction. (180°). Okay. And with that, we can now define subtraction. So how we think of subtraction, if I take the vector a minus b, we think of this as taking a and adding the negative of b. So the corresponding components for b are negated. So in the same way, if I have a here and I have b here, then minus b is going to be the same direction but opposite. And so if I have a and I add to that minus b, the resulting vector here, that's the vector a minus b. So I can have here a, there b. If instead I went in the opposite direction, minus b. So the vector that runs from the initial point of a to the final point of b, this is the vector a plus b. And if I take the vector with the initial point of a and the final point of minus b, that is the vector a minus b. And that's actually going to be important, knowing which direction a plus b points in versus a minus b. We're actually going to use that to derive some things later. So that's what subtraction means. That's how it's geometrically interpreted. And negative flips things because, yeah. Two vectors are parallel if they are scalar multiples of each other. And so a, 2a, minus 2a are all parallel. So that's parallel to that parallel. Note, here's one of the crazy things about the zero vector. 0 is parallel to every vector. The zero vector is parallel to every vector. Why? Because if I take 0 times any vector, I get the 0 vector. And so it's a scalar multiple of any vector. And so, yeah, the 0 vector, very strange. So it's parallel to every other vector, which means what direction do you point in? Everywhere and nowhere at the same time. We'll see that. Right, so if you point everywhere, you're not nowhere. Right? Friend to all is a friend to none. Okay, now we have some properties of vectors here. And now it begins. You're going to have things like this come up from now on, where every now and then we're going to put up a table of these properties, and it's going to seem painfully obvious. So we're going to tell you like, oh, a plus b is the same as b plus a, and a plus 0 is the same as a, and you're going to be like, well, duh. It turns out that when you start to talk about new objects that are not numbers, you cannot assume that all the rules that work with numbers will automatically work with those objects. For example, I just told you, you will notice that there is no a times b in this table, because that doesn't even mean anything. Like if I write AB, it means nothing, right? It's gibberish. So every now and then, you're going to see a list of rules where on one hand is going to feel very obvious, but you have to recognize that on the other hand, it's not obvious. Because if the basic rule isn't listed, it means you cannot assume that it will work. Okay, so from what we see here, vector addition works very similar to numerical addition. So a lot of the rules that we think about still work. The distributive law still works with scalar multiplication, etc. So I know some of these seem obvious, but don't think of them as obvious. Someone had to prove all of these. These were not things that were assumed. We had to actually prove this theoretically. So yeah, there are going to be times when I'm going to tell you some rules and they're going to seem very obvious, but they're not obvious. Whenever someone takes the time to actually write them down, it's not obvious, right? And pretty much students mess up because they just take their intuition from one area of math and they think that everything applies to another area of math exactly the same way. All the rules of numbers, some of them apply to vectors, not all of them. It's very important that you recognize that. So commutative addition applies to both real numbers and vectors. It doesn't apply to everything. It's very important that you know that. So these are the properties that will work just like with numbers. Now let's actually do some calculations. Suppose I have the vector A, 1, 2, 3, and the vector B, -4, 0, 5. I want you to find the following. Find the magnitude of A, find A plus B, find A minus B, find 2 times A, find 3 times B, find da, da, da. Okay, so we're going to do all these computations. Okay, so what's the magnitude of A? I mean, this point. So magnitude of A, and again, I can write either a single absolute value or a double absolute value. It really doesn't matter for us because the arrow on top indicates that we should be using the distance formula. So it's just going to be the square root of the sum of each the squares of the components. Okay, so that's going to be radical 14. Okay, not so bad. If I want to take A plus B, right? So my A is 1, 2, 3. My B is so this is taking 1, 2, 3, and then I'm adding it to -4, 0, 5. And we know about vector addition. You add the corresponding components. So it's 1 plus a -4, 2 plus a 0, 3 plus a 5. Don't have to write this line, but make sure you're adding the numbers correctly. That's how we would add vectors. A minus B, very similar. This is going to be 1, 2, 3 minus -4, 0, 5. So this is going to be 1 minus a -4, comma 2 minus 0, 3 minus 5. So we have that. You would get the same thing if you had done 1, 2, 3, and then move the -1 inside, and then added them. So this here is minus B. So this is A plus a minus B. It would have the same interpretation. So now it's 1 plus 4, 2 plus 0, 3 minus 5, and you would get the same thing. You don't have to write this line. 2 times A. This is just going to be 2 times 1, 2, 3. Which is going to be 2, 4, 6. Which is 2 times 1, 2 times 2, 2 times 3. Let me turn it down. Kept writing a recall here in case I forgot what A and B are. So 3B, that's going to be 3 times the B. Okay, 2A minus 3B. Someone tell me what that is. What's the answer? Can't have you guys just making me do everything.
14, 4, -9.
14, 4, -9. Let's see. Okay, so this is going to be 2 times 1, 2, 3, minus 3 times minus 4, 0, 5. This is going to be 2, 4, 6, say plus 12, 0, minus 15. So it's going to be 14, 4, minus 9. Yep. Okay. So, oh, and yes, someone in the comments also got that. Okay, great. I think that's all for here. Not so bad. Okay. All right. So far, the thing that you messes. I'll fix the spacing later. Thing that usually messes students up at this level, believe it or not, it's the graphing part, knowing what direction A plus B is in versus A minus B. So make sure you actually look over that. Moving on, we're going to talk about a different notation, standard basis vectors and another notation for vectors. So I'm going to introduce something called the IJK notation. And it's very important that you do not mix this notation with the angled notation that I had before. Personally, I like writing the angled notation. It takes less writing power, but you might see something written in a different way. So there is something called the basis vectors. And when you get to linear algebra, you'll know why they're called that. But pretty much, we have a bunch of vectors. Yeah. We have a bunch of vectors that looks like this. They're going to have 1 in one component, and they're going to have zeros everywhere else. Okay. So, for example, in R2, this guy, we have 2 basis vectors. So the first guy, I can call him E1, the second guy E2. And this here is E1, E2, E3 in 3 space, right? If I was in 4 space, in R4, 4 dimensions, then my E1 would be 1, 0, 0, 0. E2 would be 0, 1, 0, 0. E3 would be 0, 0, 1, 0. And E4 would be 0, 0, 0, 1. So the subscript tells you what position the 1 is in. Now, in 2 and 3 space, we call E1, E2, and E3 the I, J, and K vectors respectively. So whenever you see I, it just means the 1 is in the first component. Whenever you see J, the 1 is in the second component. And whenever you see K, the 1 is in the third component, respectively. So geometrically, essentially what this is the I vector is the vector that runs along the x-axis if I write it as a position vector with length 1. So that has I. The vector that runs along the y with length 1, that is called the j. And the vector that runs along the z with length 1, that vector is called k. Right? Now, here's something to notice. If I have some random vector here, a, notice that I can think of building up a by moving in an x direction by some scalar, then moving in the y direction by some scalar, but by some vector, then moving in the z direction, right? So this is going to be some constant times the I vector. This is going to be some constant times the j vector. And this is going to be some other constant times the k vector. So I can actually break each vector down into components based on these guys. These are called the basis vectors, and these ones are called the standard basis vectors. So ijk, these are the guys that are called the standard basis vectors. And they give us a way to interpret every vector. So notation-wise, if I have a vector a1, a2, a3, then notice that this is a1, comma 0, comma 0, plus 0, comma a2, comma 0, plus 0, comma 0, comma a3. This is true by vector addition, which we identified earlier. Now, what I can do is I can take out the scalar a1, take out the scalar a2, take out the scalar a3, and this equation is going to hold by scalar multiplication. And then the vector 1, 0, 0 is I, the vector 0, 1, 0 is j, and the vector 0, 0, 1 is k, and that holds by definition. So that gives us an alternative notation. So, for example, I can write, say, the vector 14, comma, minus 2, comma, 1. I can write that as 14i minus 2j plus k. The vector 1, 0, minus 3, I can write that as I minus 3k. Do not mix notations. Choose if you want to use the angled brackets or ijk, don't use both. So don't do something like I, comma, 2j, comma, minus 3k, right? That doesn't actually make any sense. Well, it makes sense, but now you're talking more about tensors as opposed to vectors. It has that's a whole other meaning. So for us, that's not a vector, okay? So, right. So this is a different notation for vectors, the ijk notation. And theoretically, basis vectors are very important to be able to dissect vectors in this way ends up being very useful. Okay, unit vectors, the last thing I want to talk about in this section, and then I'll kind of just introduce the ideas that we're going to be using in the next couple sections, is the idea of a unit vector. So now a unit vector is simply a vector with length 1. That's it. If a vector has length 1, we call it a unit vector. So if a vector is not the 0 vector, then a unit vector in the same direction as that vector, should be an A here. Unit vector in the same direction as A is given by this equation. Just take a vector and scale it by its magnitude. So if I take a vector of length 2 and I divide it by 2, then it will actually become a vector of length 1 because I can scale it by just dividing by its magnitude. Okay. So for example, let's say I have a vector 2, -1, 3, and I want to find 2 unit vectors that are parallel to this vector. Okay. So here, A is 2, -1, 3. Then U is going to be, well, A divided by the magnitude of A. So that's going to be 2 -1, 3 divided by the magnitude of that. So that's what, radical 14. So this is 1 unit vector in the direction of A. What's another one? Well, according to the instructions, parallel to A. Tell me another unit vector parallel to A.
If you just change the sign on each of those components, wouldn't it be parallel?
Right, you take the negative, right? So by multiplying by -1, you flip the direction, which according to us is parallel, and it also has length 1 because we're multiplying by -1. So the other one is minus U. So here I can have the vector A, and then what we just saw, we just created a vector U. So this is U, and we also created a vector minus U. So the length here is square root of 14, while the length here is 1. And the length here is also 1, and it's parallel. There are going to be times when we want a unit vector in a certain direction, because we're going to want to do some math computations in that direction, but we don't want to scale our computation. So finding a unit vector is going to be very important for things of that sort. So there are times we know that multiplying by numbers scale things, so we can get the wrong answer if we're scaling things in ways that we shouldn't be scaling them. So sometimes we have operations with vectors. We want to do it with unit vectors as opposed to regular vectors. And that's the vector section. Any questions on that? Are we good? Everyone followed? So I know people who are doing physics are obviously knew all this. But what I want to do now, just take 10, 15 minutes to just pave the way for the next topic.
I have a quick question.
Yes.
So for the vectors, are you going to tell us which notation to use, or can we just decide which one we like better?
You can decide. But of course, if I give you a problem, I might use different notations in a problem. You should just know how to interpret it.
Okay.
But in general, I don't care
these
what
going to
notation you
be-
use. Yeah.
Are these going to be on Friday's test or just on the final?
Everything I did up to today is on the test. So yeah, for the test, you need everything up to 12.2. Dun, dun, dun. Now we're going to talk about vector products. So I mentioned that there was no analogous operation like multiplication for vectors, but there are products that we can take for vectors. So there's something called the dot product, and there's something called the cross product. Now, I'm not going to actually tell you what these guys are, but I'm going to introduce why such products might be useful. So we need other ways to combine vectors. And the dot product is a way to combine two vectors and get a scalar. The cross product is a way to combine two three-dimensional vectors and get another vector. And these scalars and vectors are going to be useful in very particular ways. So now I just want to introduce the idea of why these guys would be useful and also motivate their definitions. So in three dimensions, so starting next class, you're going to be looking at objects like this. So like a surface, right? So you're not just looking at a curve now or a line, you're looking at a surface. And we might want to talk about surfaces, right? And like I said, a vector is going to be nice ways to talk about a surface. So I can look at a single point as I can identify points on this guy by, a vector emanating from the origin, and I can describe the surface in terms of vectors. So I can know where things are on this thing. Other than that, now you want to get to the idea of, we haven't spoken about calculus yet. So we introduced the three-dimensional space, and now we know about vectors. So know how to locate things in our space, how to define regions in our space, how to do things like that. But what happens when we want to do calculus? What if we want to differentiate and integrate in our space? What would we need to be able to do? That is going to be important. So for example, what are the important ideas in calculus, the derivative and the integral? What is the derivative useful for? Well, it tells us about slope. What is slope useful for? Well, it's an idea of direction, right? I can tell when something's going up or down, and I can know what direction something is moving in, is if it's increasing or decreasing. So direction is obviously very important. And you might think just knowing about vector directions is going to be enough, but it's not. And I'll explain why pretty soon. When it comes to integration, what do we need to be able to do? Well, we did integration by setting up Riemann sums. So if I had the x and y axis and I had a curve and I want to find the area under the curve, what did I do? Well, I took a section of the x-axis, I diced it up into little pieces, and on each piece I erected a rectangle. So it turns out, if I want to find the higher dimensional analog to that, that would be volume. And how are we going to do that? Well, in the same way, we're going to take, we are going to take, so domain of some function, I'm going to want to dice it up into separate sections. And then I'm going to want to erect these boxes. And then I'm going to interpret the volume under that curve as the sum of the volumes of all these boxes. So we need to be able to do all these things, right? So I need to be able to talk about the direction of these things. So by emanating these guys up, I can dissect a surface like this. So a surface like this could be represented by something like fz equals f of xy, where f of xy is just some function of x and y. So for a particular coordinate, if I plug in the x and y coordinate, then this function tells me what the corresponding z coordinate is going to be. And this is one way I can visualize a surface. There's a vector way, but this is more of a scalar way of visualizing a surface, right? But now when it comes to doing calculus, I not only want to talk about how to identify the points on this surface, but I want to be able to talk about how would I go about dissecting a surface and finding the area of the dissections, right? So in the same way, when we had in 2 dimensions, to find an integral, I needed to dissect the x-axis. Now, notice that I need a way to dissect the xy plane. And then I need a way to measure the dissection. So that was delta x. So there's going to be a way I need to measure the change across a dissection, which now is not a length, it's an area. So I need to measure areas of these patches. And I also need to talk about the direction in which that patch is slanted in space, right? To be able to do calculus, I have to be able to do those 2 things. Right? If I can't talk about how I'm going to dissect a patch and find the area of the patch so that I can set up these rectangles, integration is done. It can't be done. If I can't talk about what direction a patch is slanted in space, differentiation is done, can't be done. How are you going to talk about slope and direction? We need to be able to talk about these things. So there are 2 ideas that are very important, right? So we need to be able to talk about the direction of a patch and the area of a patch. Right? And this is actually where the dot product and the cross product comes in. This is why we invented them. We needed to be able to do sophisticated things like calculus in 3 space. So let's say here is a patch. So here's a patch. Right? So let's say I took one of these patches, like I took one of these patches, you know, like this guy right here. You know, and I moved him down to here, right? So that's that patch. We'd like to know, important, we need to be able to find the area and direction of slant of this patch. Right? So very important. Calculus is dead if we can't do these 2 things. So how do you go about finding the area of a patch? Well, we just learned about vectors, so let's actually put them to some use, right? So suppose I call this vector here A, and I call this vector here B. It turns out that I can use my knowledge of A and B to actually talk about the area of this patch. Well, how do I go about the area? Well, look at the vectors A and B. So here's the patch again. So A is running along this side, B is running along that side. Here's how we're going to go about finding the area. I'm going to cut this into 2 parts, cut it into the diagonal. So now I have this thing here. And let's suppose we know the angle between A and B. Now, I know right now you don't know the angle between A and B. I will show you guys how to find that later. In fact, that's what the dot product is all about. The dot product is a way to find the angle. How do we go about finding the area? Well, the area is just going to be double the area of this triangle, right? Because I split that patch into 2 triangles. Okay, so my high school geometry people, I have this triangle here. I obviously would know the length of 2 sides. So if I know A, I would know the magnitude of A and the magnitude of B, right? How do I find the area of a triangle if I know two sides and an included angle? That's right. Half AB sine theta. Okay, so that's one of the formulas for the area of a triangle. So it turns out the magnitude of A, magnitude of B, sine theta actually tells me the area of the patch. So that's going to be useful, right? So we have this equation, right? So provided that I can find the angle between the vectors along a patch, I can find the area. I can just use this equation. And in fact, this equation is going to be very important. We're going to come back to this in the next section because that's what the cross product is about. So the cross product is going to use this fact. Now, how do we actually find the angle is the question, right? So yeah, I can find the area by this way if I know the angle, but how do we find the angle? So let's create another triangle. So let's say here's A, here is B, and here is C. What is the vector C in terms of A and B? This is from the last section. It turns out that C can be described in terms of A and B. Eric?
So what was the question again?
Describe the vector C. So again, I started out with this patch A and B, and then I connected their edges and I wrote, called that C. Can you describe the vector C in terms of the vectors A and B? So I have a guess that it's B minus A. What would B minus A look like? B minus A means I move in the direction of B, and then I move in the negative direction of A. So B minus A is a vector that's in this direction. Is that what we want?
It's A minus B.
It's A minus B, right? So this is what I was talking about for you guys. So I know it seems like what I was doing was easy, but if you're not paying attention, it'll actually trip you up. This is actually the vector A minus B. Okay, so now what we know is I have a triangle with an included angle. I know the magnitude of this side. I know the magnitude of this side. And now I actually know the magnitude of this side. Can I find the angle? So I know the two vectors that are along the patch. How could I find the angle between them? Ideas? I know the three sides of a triangle, and I want to find the angle in between them. I know it's been a while. That's right, law of cosines. That's how we find the angle. Okay, so if I want the angle and I know all the sides, I can use the law of cosines. Law of cosines can be used on any angle, so that's what it is. So for our above patch, so if I'm in this scenario where I know this has magnitude of A, let me just use one, magnitude of B, magnitude of A minus B, and here is theta, then by law of cosines, A minus B squared is going to be equal to A squared plus B squared minus 2AB cosine theta. And then I would be able to find theta by, well, it's just going to be equal to the cosine inverse of a squared plus b squared minus a minus b squared all over 2ab. Okay. So if I know the two vectors that describe a patch, I can find the angle between them by this equation. And I know how to find the area of that patch by this equation. Now, it turns out that the dot product and the cross product are actually intimately acquainted with these equations, which usually no one tells you about, but it's true. So now let's talk about direction. Direction is the next important thing. So notice that we just solved the area problem. Well, one of the area problems. So integration is saved, right? I know how to find the area of all these things now in terms of vectors. So we're pretty sure we can set up integration. Now, how do we set up differentiation? What about direction? How do we define the direction of a patch? So here, I'm in 3 space. And once I describe this, the direction of the patch, we're going to end there. I know we're going over time a little bit, but right now we're just talking. I'm not going to test you on this directly, but I just want to see you to see where things are coming from. So here's the patch in space, floating in space. How can I talk about the direction of that patch? Right? So we just spoke about vectors, and I said, oh, vectors are awesome. So you might think, well, I can describe the direction of this patch using a vectors. How do we find the direction of slant of this patch? So an idea is to use vectors, because I just told you vectors have direction built in. So if I'm going to describe a direction, it would be nice to use a vector. But which? Okay. So I know that the direction of a line, so if I'm in 2 space and I want to talk about the direction of a line, I can just use a vector that's parallel to that line, right? And that's another way I can describe the slope, by describing a vector that's parallel to the line. But now I'm in 3 space. So what vector am I going to use here? So you might guess a parallel vector. But the answer is no. It turns out that if you tell me a vector that's parallel, it does not give me a direction. And someone said perpendicular. Yes, that is in fact the answer. Now, why is that the answer? So I think I actually want to illustrate that to you guys if you haven't already, if you don't already see it. And I had, oh, let's use a book. I really like this book, by the way. So this is my patch, right? It's floating in space. Just it's a 2-dimensional rectangular-ish thing, parallel thing. The reason why, if you told me a vector that was equal to this patch, would be useless because, well, that is also parallel. That is also parallel. That is also parallel, right? There are an infinite number of vectors that are parallel to this patch. So I wouldn't be able to pinpoint a vector that everyone would agree on without a lot of work to check it. On top of that, even if I pick one vector and say, you know what, everyone agree, let's use this vector. This vector is parallel to the patch, but it's also parallel to this patch. And it's also parallel to this patch, right? There'll actually be an infinite number of patches that is parallel to any individual vector. So parallel vectors aren't good. So now you might start thinking, okay, so we need the vector to poke out of the patch somehow. And you'd realize that no matter what angle you pick, there would be the same problem, except one angle. So if I used a 30-degree vector poking out at 30 degrees, well, there are tons of vectors that poke out at 30 degrees, right? So still not useful as a definition of direction. However, there's one angle that does not have that problem, and that is the 90-degree angle. You see, no matter where on this plane that I put such a vector, remember, the position of the vector does not matter, the magnitude and direction. The perpendicular direction is not changing. No matter where it is, it's always pointing in the same. The only variable would be pointing in direct opposition. However, that's parallel. It's just going to be a scalar multiple of this guy. So it turns out a perpendicular vector is going to be what we want. So we need to be able to find a vector that is perpendicular to a patch. Now you might say, well, how do you find a vector that's perpendicular to a patch? Well, there's one thing you have to be aware of. You might say, okay, well, now we can use a parallel vector to the patch and then just find a vector that's perpendicular to that. That wouldn't solve the problem because here's my vector in space. Here's a vector perpendicular. But look, this is also a vector that's perpendicular. This is also a vector that's perpendicular. This is also a right? There's an infinite number of vectors that is perpendicular to any individual vector. So it turns out perpendicular in 3 dimensions is not unique. In 2 space it was, in 3 space it's not. So if I had a vector in 2D, there was only one other direction that's perpendicular to that and the opposite, right? In 3 space though, this is not true. There's an infinite number of vectors that are perpendicular to any given vector. So if I have a vector that's parallel to something and I want to pinpoint a vector that's particularly perpendicular to the patch, it's not good enough to have just one vector parallel to the patch because I can't determine which one, because all of these guys are perpendicular to that vector. So how do you solve that problem? Well, the answer is to actually get a third vector to help you out. If instead I can find 2 vectors that are parallel to a patch that are not pointing in the same direction, and I can find a third vector that is perpendicular to both at the same time, it turns out that that vector would necessarily be perpendicular to the patch itself. Now, why would that be perpendicular to the patch itself? Because the moment I try to break perpendicular to one of them, I can maintain perpendicular to the blue vector, but unless I'm perpendicular to the patch, I would lose the perpendicularness to the red vector, right? So being perpendicular in higher dimensions is very tricky. And so for that reason, we give it a whole other name, in fact. Perpendicular, we don't say perpendicular in higher dimensions. We use the word orthogonal. So we can say 2 vectors are orthogonal means they're perpendicular. They meet at 90 degrees. However, this can be done in an infinite number of ways. So to actually break things down to more specificity, we need a bunch of vectors to talk about being perpendicular or orthogonal to a particular direction. So it turns out being able to find 2 vectors in a plane and then computing a third vector that's perpendicular to both of them is going to be very important, because once I'm able to find such a vector, I can now talk about the direction of that patch. Once I can talk about the direction of the patch, I can describe slope. Now the derivative is back in play. I can do calculus. I can do all sorts of things. So we need to be able to find the angle between 2 vectors. That is going to lead us to being able to find the area of a patch, which is going to help with integration. The dot product is a way to compute the angle between vectors. So the dot product is going to be a way, take 2 vectors, it's going to give me a scalar from which I can figure out the angle between those 2 vectors. That's the dot product. That's what it's for. And then on the flip, on another scenario, give me 2 vectors. I need to find a way to combine these 2 vectors to create a orthogonal vector. That is what the cross product is about. So a cross product is a way to combine 2 vectors and get another vector as an output where that vector is orthogonal to the 2 original vectors. A dot product is combining two vectors to get a scalar, where from that scalar, I can figure out the angle between the two vectors. Once we have the angle and the direction, we have calculus. And so that's why these guys are actually important. So hopefully that kind of illustrated to you why we actually care about it. So the actual, so the real answer, find a vector that is orthogonal to the patch. And just remember, orthogonal is just a more comprehensive term for perpendicular. Kind of like how derivative is a more comprehensive term for slope. Whenever someone says slope, they're talking about the direction of a line specifically. When we say derivative, we're talking about direction of any curve, almost any curve, right? Any differentiable curve, okay? So derivative is a more comprehensive version of slope. In that same way, orthogonal is a more comprehensive version of perpendicular. So such a vector is called a normal vector. So the answer is to find the normal vector. Okay, and so that actually leads us to, well, if we had more time, this is the guess right here. Let me create some space for this. So if I want to find a vector that's orthogonal to the patch, what I can do is find the vector A and B that are running along the edges of the patch and find a vector that we call the normal vector. Or I can do the opposite, right? It's not going to matter. So N is orthogonal to both A and B. Okay, so that's what we're going to be doing moving forward. And that's what the dot product and cross product is going to help us with. So hopefully I convince you that being able to do this is important. Being able to find the angle between two vectors is important, because then I can find the area of the patch that they surround. Once I have area, I now have a way to dissect the domain space of a three-dimensional surface, of a two-dimensional surface, which now gives me integration. Once I have that, now I want to talk about differentiation. For differentiation, I need to describe direction in some way. How do I define the direction of some surface? Well, find a normal vector to that surface, and that defines direction. And then we're going to be able to talk about derivatives in terms of these directions and directional derivatives and things of that sort. So that's where you're going to be going in the next class. But I'm actually going to show you how do we actually go about computing these two things. And that's the dot product and the cross product. So the cross product is going to be a way to find the vector n. The magnitude of the vector that I'm going to find is actually going to be equal to the area of the patch. And the dot product is going to be a way to find the angle between the two vectors. So it's going to be a scalar. And that's what we're going to start on Thursday. It's going to be exciting stuff. But I didn't want to just give you the direct definition, which looks like this. I kind of wanted you to see where it's coming from and why the formula actually makes sense, which you've probably never seen. So that's why it's important. But yeah, we are going to wrap up there. I know it's been over time, but it's been a long time since I've seen you guys. And I think we'll stop there if there are no questions.
I have a question.
So, no questions?
I have a question. Will we
Sure.
have Will we have homework for vectors that'll be available and or due before the test on Friday?
No, I'll put up some homework problems, but I won't make it due before the test.
Okay, thank you.
I'd rather you prioritize studying for the test over finishing homework. Homework might be helpful to do that, but it's not like the only thing, you know? So yeah, if I didn't put up vector homeworks yet, I will. I believe I have all the homeworks for series up already. So yeah, I will get to that. But we're going to stop there for now. So thank you for your attention. And I will see you guys in the next one. If you have any more questions, you can email me or put it on Piazza, as I mentioned. And hopefully you guys are getting along in your groups. We will stop there for now. So without further ado, I'll see you guys in the next one. Ciao.